Hello everyone, welcome to IMS GATE Academy. So we are discussing our fluid mechanics in the foundation course, and we have already covered the subject topics like fluid dynamics, kinematics and properties of fluid, and also the statics part, right? Now in the previous class actually we have covered our topics, okay, that is related to flow through pipes, right, in which we have discussed about the loss of head when the fluid is flowing through pipes. So those points we have discussed, and in that first of all we have discussed about the major losses and then the minor losses, and I hope you remember all the concepts related to that. Okay, like major loss is what? Because of friction, right? Because of the friction, because of frictional resistance. And if I talk about the minor losses, it is because of the change in velocity. Either the magnitude of velocity can be changed or the direction of velocity can be changed. So those points we need to understand, and various cases we have discussed for the minor losses, and also how to calculate those losses. And for major loss specifically, we discussed about the Darcy-Weisbach equation, in which the formula is FLV square by 2dg, and the most important part is we need to understand is the friction factor calculation. Based on type of fluid flow, the friction factor value will change. Okay, so we need to first of all calculate or understand the value of friction factor, then only we'll be able to calculate the head losses, right? Now topic for today's session is hydraulic gradient line and a total energy line. Okay, now what are these lines? Okay, what actually this line will represent? So those things we will discuss here, and we'll talk about what will be the application of the lines like HGL in short we can say, and TEL, total energy lines. So like it is a representation, okay, it is nothing but the graphical representation of energies, okay, and mostly it is used in flow through pipes. Okay, so we'll graphically represent the variation of energies, okay, variation of energies at various locations, okay, at various locations. What are the variation of energies that we will see here? Now first of all we'll discuss about what is HGL, then we'll discuss about TL, and we'll see some numericals related to that also. Okay everyone, now see, so first of all this point, okay, right. So concept of hydraulic gradient, okay, and this HGL and this TL is basically a graphical representation of the sum of different heads. Heads basically representation of another, like what, energy only. Heads is what, like energy representation, okay. So usually we'll represent the energy in terms of head. So it is a sum of different heads along the length of the pipe, right? And it is mostly used in the study of flow through pipes. That is what the concept of HGL and TL. Now one by one we will discuss HGL and then we'll discuss about TEL also. So this is most important point, the graphical representation. This thing you should understand. Okay, now see. Okay, so this is the general diagram in which we will have HGL and TEL. Now from this diagram you can understand what is HGL and what is EGL, energy gradient line, or TEL also we can write, total energy line also. Now this diagram is what very important. See here everyone. So as the fluid flows from here to here, now see what are the heads we are having. If you know the Bernoulli's equation, you know about first of all this pressure head, okay, this kinetic head, and this is what the datum head. So all three energy heads, I hope you remember. Okay, all three heads, if you remember, in the Bernoulli's equation we have discussed about pressure head, kinetic head, and the datum head. Now we will see the values of this head. Now across the, or basically we'll go along the length of the pipe. If we see, so let's suppose this is the location 1, okay. Now with the help of piezometer, we will be able to identify what? The head. Which head? The piezometer head. So piezometer head basically sum of pressure head, static pressure head plus the datum head. Okay, with the help of pitot tube you will be able to get what? The kinetic head also. Okay, we'll get the kinetic head also. So with the help of piezometer, see this is the point, okay, for this point this is the piezometer head. So this much head will represent what? pressure head plus the datum head. So any reference datum we can have. Let's suppose this is the datum we are having or the reference. So this piezometer tube will tell us the pressure head plus datum head, right? Similarly, let's suppose this is the location 2 and at this point this pressure plus datum head is like this. Now if I join these points, and not only these points, along the length there are different number of points. For every point, if I plot the piezometer head, okay, I will be getting the individual points. Now if all the points if I join with the line, okay, if all the points if I join with the line, then that particular line will be hydraulic gradient line, HGL. Hi Pragya. Okay, I hope this point everyone understands. So at every location along the length of pipe, at every location if I observe the piezometer head, okay, piezometer head, okay, so if I just plot the piezometer head only for at every location of the pipe, and I will be getting every location, just join all those points, you will be having a one line. That line is itself known as HGL, hydraulic gradient line. Now same thing we will do for total energy line. In total energy line, apart from static pressure head plus the datum head, kinetic head also involves. So in order to calculate the kinetic head, we will be using pitot tube. Okay, we will be using pitot tube. So if we use pitot tube, the difference of piezometer head and a pitot tube will give you the kinetic head. Will give you the kinetic head. So this is what we are having as kinetic head. Correct? So difference of piezometer and pitot tube will give you the kinetic head. This is kinetic head at location 1. Similarly, here also it will give you the kinetic head. Okay, correct. So these points are what very important. So now using this line, I can have an idea like how the piezometric head is what changing and how our total energy head, okay, is changing during the fluid flow along the pipe, along the length of the pipe. So basically, I hope like this point is clear. At every location of the pipe, if you have the piezometric head or the total energy head, just show all those points at every location of the pipe. At every location of the pipe, you will show all the points and just join all those points. You will be having the lines. Now you will be seeing here a very important point. The HGL is what rising, but the total energy line is what horizontal. So actually in this case, we have not assumed the losses. That's why the total energy will remain constant. Are you getting the point? The total energy will remain constant because in this particular case, I have not assumed the frictional losses. Okay, no head loss I have assumed. So that's why the total energy line has to be horizontal. It should have a same value at every location. At every location of the pipe, the value of total energy head, which include all these three, will be what? Constant. So that's why this is horizontal. But if I talk about the HGL, it is what? Rising. So it means the piezometric head is what? Increasing if I move from location 1 to location 2. That is what the observation. So using these lines, we can have a point and we can have an understanding how the variation of energies are there. Just by these diagram only, we'll be able to understand that things. Correct? I hope this point is clear. So this is what the basic general diagram. Now one by one, I will give you the definitions of HGL also, TEL also, right? Okay, just we'll move to the second point, that is HGL. Now see here, line joining the piezometric head. Okay, and remember earlier also we have discussed this thing. Piezometric head is the sum of pressure head plus the datum head at various points in a flow along the length of the pipe. This is very important. Okay, with respect to some reference line or the datum, or you can mention datum also. Now see, so your HGL equals to pressure head plus datum head, right? So that is what HGL we are having. Sir, these two may intersect at anywhere. See, Pragya, see, very interesting question you have asked, like whether they will intersect or not, both the lines. Now see here, where this line can intersect, or can I say like where this HGL and this total energy line can be same. So for that you need to understand, see, the total energy line is having three components: pressure, kinetic and datum. Okay, so HGL, pressure plus datum. So this, you first of all you need to locate, or you have to identify the values of this one. So at any particular location you will plot these values and just join all those values, you will be getting the HGL. In a similar manner, see, TEL, total energy line. So here total head I will be taking here. So simply if I have to write, it will be pressure plus kinetic plus datum, correct? So this is there. So all of these energies we need to identify first of all, and we will calculate, okay? And at any particular location we will see the value of this total energy head and will graphically locate, and for every section along the pipe length we will plot all those values, and then finally we will join this value, join all those points, and we will be getting the total energy line, correct? I hope the point is clear, everyone. Right, so just one example if I show you here. So let's suppose this is the pipe you are having. Okay, now see. Now pitot tube, if I apply here, pitot tubes. So okay, now see. So let's suppose this is the location 1. This is location 2, right? This is location 1 and this is location 2, and this is what the fluid flow, okay, along the pipe. Now very interesting point here. Let's suppose in this piezometer it will rise like this, and here it will rise, let's suppose, up to here. So this point is actually what? The piezometric head for you, right? And this is what the piezometric head at point 2. So what I will do here, simply I will join these 2 points. I will simply join these 2 points. So this will be what? My HGL, hydraulic gradient line. Now if I ask you what will be the total energy line, you will say, sir, in HGL pressure plus datum are there, but in the total energy line kinetic is also involved. So obviously it will be above of HGL only, right? So if I have to draw the TEL also, so how I will draw? Somewhere here it will be like this. Okay. Now see, this is TEL. Now the difference between these two will be what? Kinetic head, that is V square by 2G. Okay, right? So this is what the representation, okay, this is what the representation we are having for the gradient lines, hydraulic gradient lines and the total energy lines, right? So a few important points we will be writing here, okay, a few important points for HGL and TEL, right? So first of all we will see the observations from this diagram itself. The difference of HGL and TL will be kinetic head always, okay. Now wherever these lines are what intersecting or they are coinciding, it means kinetic head is not there, okay. The value of kinetic head is what? 0 simply, okay. So this point you should understand, okay. Now one more thing, like TL always above of HGL, obviously, because it is having total energy heads. HGL is not having the kinetic head, that's why it is below the TL. during the fluid flow, TL always drop because of the losses. As the fluid flows from section 1 to 2, there will be always some losses, and because of that, total energy head is going to decrease. But the HGL may increase or decrease depending upon the pressure changes, right? We will see some examples here in which HGL may rise or drop also. So HGL will increase or decrease, or it will rise or drop. It depends upon the pressure changes values, right? And TL always drop because of the losses. But let's suppose some external pump if I've installed in the pipe, and because of that, what is happening? It provides the energy to the system. So because of that, TL will rise, okay? But without any external help or support, this TL, total energy line, can never rise. It will always drop along the fluid flow because some losses will be there. But if I install any pump, obviously it will supply some energy, and because of that energy, it will rise, total energy line. Okay, everyone? So that is what the important concept here. Now, we will see here some important note points. Important points regarding HGL and TEL. Okay. Regarding HGL and TL. So, what is the first point? Okay. First point, simply I will write the relation. Pressure plus datum. Whereas in TEL, it is like summation of all the energy forms. Correct? Now, point number 2. TL is always above HGL. Always above HGL. Right? Correct? Because it is having all the energy forms. So that's why it will always above the HGL. Okay. Now, TL always drop during the fluid flow. Always drop in the direction of fluid flow. TL always drop in the direction of fluid flow because of losses. Because of losses. But if any pump is provided, pump, okay, and remember this thing, it is external. Pump is provided, then if pump is provided, then what will happen? TL will rise. TL will rise. Okay. I hope the point is clear. TL always drop in the direction of fluid flow because of losses. And but if pump is provided, that is what external, okay, then TL will rise. That is the only possibility. Okay. Now next point. HGL may rise or fall depending upon piezometric head. Depending upon piezometric head. Correct? correct. And one more thing, the observation from here in the previous diagram, the vertical intercept between TL and HGL is kinetic head. Vertical intercept between TL is kinetic head, which is V square by 2G. Right. So all these 5 points you need to remember, okay, for HGL and TEL. Correct? Any doubts in this one? Tell me, everyone. Correct. Now I will ask you regarding the HGL and TL based on the cross sectional change in the pipe, right? Okay. Now see, let's suppose there is a pipe here. Okay. Now let's suppose this is the pipe flow we are having. Okay. Now see, in this particular case, let's suppose this is the fluid flow. Now this is a case of sudden contraction. This is a case of sudden contraction. Sudden contraction. Now for such cases, how you will draw HGL and TL? Tell me. What will happen to HGL and TL? Any idea? Any idea regarding the sudden contraction case? How the HGL and TL will change? Okay. Now see, very interesting point. So if I take any datum, so for the datum point, it will be same because it is horizontal one. So datum point will be same. Now depends upon the pressure changes. If I consider a point here, that is point 1 here and point 2 here. So obviously V1 value will be less than V2 because the cross-sectional area for section 2 is what less, so velocity will be higher. And accordingly, and because of that, what will happen? Pressure at 1 will be what more as compared to pressure P2. Correct? I hope the point is clear. So velocity is what more, okay, velocity will be what more at point 2, but the pressure will be less. Okay, here velocity is less, but the pressure is what more. Velocity at 1 will be what less, but the pressure is what more. Now, what is happening when we just move from 1 to 2? Pressure decreases, and if pressure decreases, HL will drop. HGL will drop here. Okay. Now see how it will be there. I will draw the HGL and TL here. Okay. Now see. Okay. So first of all, total energy line. Obviously, it will decrease along the fluid flow. Then suddenly, because of the losses, it will drop like this. Okay. Now for HGL, it will also drop. Okay. Then finally, it will be like this. So now you should understand the change in the TL is what the total losses. But change in HGL will tell you what? Change in piezometric head. Change in piezometric head. Right. So this point you need to understand. So this is what we are having, HGL. Okay. This is HG. Okay. This is total energy line. Total energy line, and this is HGL. So how we have drawn this point, you need to understand, very important point. During the fluid flow, the TL always drop, but actually what happens, because of this sudden contraction, energy losses will be there, okay, because flow separation, eddy formation, right, all those things we have discussed in the last class also. But what happens to HGL, as the pressure increases, pressure decreases actually, because section 1 to 2 if you go, velocity increase, so velocity increase, pressure decreases, okay. So I can just mention the point here also, velocity less, pressure is what? High. And here what will happen? Velocity is more, pressure is what? High. Pressure is what? Low here. Okay, so just from Bernoulli's equation we can understand, velocity less, pressure is high, velocity more, pressure low. Okay, velocity high, pressure will be low. So pressure, as the pressure decreases in the section 2, so HGL will drop here. HGL will drop. But let's suppose if I draw the sudden expansion case. Next, sudden expansion case, if I see, sudden expansion, okay, if I see the sudden expansion, yes Manjit, absolutely correct, TL will always decrease, and the reason I have discussed here, like what is the reason? Because of the losses, because as the fluid flows, losses will be there, and because of the losses, total energy line will consist of all the energy forms, it will decrease obviously, correct? Tell me Manjit, it is correct, yes or no? Correct, okay. If you use pump, then yes, absolutely correct. If you use pump, then definitely it will increase. So if pump, that is what, but remember the point, it is external to the system. If provided, then TL will rise. Correct. So now, see, we have discussed about sudden contraction case. This is the variation of energy lines in TL and HGL. But if I talk about sudden expansion case, what will happen? Okay, so I will first of all draw the sudden expansion case here. Right, now in such cases, what will be there? How the sudden expansion case will be there if I talk about HGL or TEL? See, so first of all, if I analyze simply point 1, point 2, okay, so at section 1, velocity will be what? More, okay, if I see the velocity, so simply if I see velocity and pressure, if I see in section 1 and section 2, so in section 1, velocity will be definitely high, pressure, okay, pressure will be low. But in section 2, velocity decreases, pressure increases. Correct? So as the fluid moves from 1 to 2, the pressure is increasing because the velocity has decreased. So pressure has to increase, right? So this is what, very simple, right? There is no, like, always, sometimes I know like students will have a confusion regarding this thing. So don't be confused about that. Simply understand the continuity principle and the Bernoulli's principle. So when the fluid flows from 1 to 2, how the velocity will behave? Velocity is going to what? Decrease. And as an effect from the Bernoulli's equation, we can say pressure is going to increase. Now, if the pressure is going to increase, HGL will rise, right? So now I will just draw the lines here. Okay, so first of all, TL. Okay, TEL, first of all, TEL. Drop because of the losses. Losses will be there because of sudden expansion, right? Now, second case, there will be rise, correct? Rise because the pressure is what? Increasing. This is TEL, this is HGL. Correct? Yes or no? Any doubts? Correct. Now, see what will happen. I will show you here this thing. So, this part will tell us H loss. Okay, due to expansion. Okay, and previously this drop will tell you head loss due to contraction. Due to contraction. Correct? So this drop in the total energy line will represent the losses, okay, because of this contraction, and in the case of expansion it will be like this. Correct? Very, very important points, guys. Very important points. Okay. So I like, okay, I hope like everything is clear regarding the HGL and the TL. Okay, there will not be any doubts. Yes or no? Just tell me. Okay. Now we'll move on to the numerical parts. Okay. Now we'll discuss some numerical. Yes, this is the first numerical. Okay. So just solve this one. Okay. So this is pressure drop. Okay. So this is pressure drops. Okay, read the question. When a sudden contraction from 60 centimeter diameter to 30 centimeter is introduced in a horizontal pipeline, the pressure drops from 100 kilopascal at the upstream of the contraction to 80 kilopascal on the downstream. CC, coefficient of contraction they have given, right? Find the flow rate. So discharge they are actually asking. Just try and tell me what will be the answer, everyone. Okay, so sudden contraction case. So first of all, we'll draw the diagram here. Okay, sudden contraction case. Now see, so what they have mentioned, 60, this is 60 centimeter, okay, and this is the 30 centimeter. Pressure drop from 100 to 80 kilopascal. Correct. 60 centimeter to 30 centimeter change is there, 100 kilopascal to 80 kilopascal, like that they have mentioned. Coefficient of contraction they have mentioned cc 0.65. Now if you remember, in the last class we've already covered the case how to calculate the losses here, okay, but before calculating the losses, first of all I will apply the Bernoulli's equation. See, in order to calculate the discharge, I need what? Area into velocity, okay, area into velocity is there. If I know the velocity, I will be easily getting the answer of discharge also. So if I apply the Bernoulli's equation, so let's suppose this is 0.1, this is 0.2. So Bernoulli's equation if I apply, plus losses, so it is horizontal, right? If it is horizontal, so we will directly cancel out the z1 z2, right? Now very important point, P1 and P2 they have given V1 square minus V2 square divided by 2G. The pressure change is what? 20 kilopascal, 20 into 10 to the power 3. So density is 1000 into G equals to H losses. Now H losses, what is the formula? If you remember, it is V2 square by 2G 1 by Cc minus 1 whole square. Correct? 1 by Cc minus 1 whole square. This is the formula. Now V1, V2, Cc value is what given in the question. V1, V2 are the what? Unknowns. Now one more relation we can have, because continuity equation, if I use the continuity equation, so I can easily get the relation between V1 and V2 also. Okay, so from continuity equation, area A1 V1 equals to area A2 V2. Okay, area, okay, simply I will write pi by 4 into 0.6 square into V1, pi by 4 into 0.3 square into V2. Now from this I will be having a relation between V1 and V2. So that relation I will be utilizing here, and I will get the value of V1 or V2. Now if I know the V1, V2 and the diameters are what directly given, I will easily get the discharge also, right? So in this question, multiple equations we need to apply here, then only it is possible to calculate the discharge here. I hope the question is clear, everyone. Yes. So simply they have mentioned the dia, pressure changes they have mentioned, Cc value they have mentioned. Now they are asking the discharge. Okay, or even they can also ask simply the loss also, the loss because of the sudden contraction. So in that case also directly formula we can apply, but still V2 value is not known to us. V2 value is not known to us, no. So then how we can calculate the losses also? So we have to apply first of all the Bernoulli's equation, then continuity equation, and using both the relations I will be getting one of the unknown values like V1 or V2. Using that unknown value I can easily get the discharge also. Correct? So just solve this one and tell me what will be the answer. Done everyone? Tell me what will be the answer. Okay. So using the relation V1 and V2, because from that we'll have a relation V1 as V2. Okay. Something as a V2 you will be having using both the equations. Equation 1 and equation 2. From 1 and 2 we'll be having the one of the values of velocity. Okay, from equation 1 and 2 we can easily get the velocities V1, V2, and finally we'll be having the discharge. Okay, so the discharge value, the final answer, that is coming out to be 0.403 meter cube per second, and the loss because of the sudden contraction is coming out to be 0.48 meter. So that will be the answer, but the concept you should remember, like how we can calculate the discharge also. Correct? Yes or no? Now moving to the next numerical, guys. Next numerical. Okay. Now this is what the interesting problem, right? So at a sudden expansion of a water pipe from a diameter of 0.25 meter to 0.48 meter, HGL rises by 10 mm. Then find the discharge. Okay. So that is what a very interesting question it is. Now see how we can solve this one also. So here it is sudden expansion. So it will be like this. Right, now see, here it is 0.24 meter and here it is 0.48 meter. HGL rises by 10 mm. So HGL, okay, then like this it will be there. So rise of HGL is defined by simply, so if I have to apply the Bernoulli's equation, let's suppose this is section 1, section 2. If I simply apply the Bernoulli's equation, see everyone, H losses, correct? Now if this is clear, so now what I will be writing here, okay, now okay, so what they have mentioned, okay, HGL rises by 10 mm. So how we can represent this data in this equation, Bernoulli's equation, how I can represent this data? HGL rises by 10 mm, right? Now see here, HGL rises by 10 mm. So simply P1, okay, so we'll write like this, P2 plus Z2 minus P1 plus Z1, okay, and here it will be like this. V1 square minus V2 square by 2G plus losses, whatever the losses are there. This value, the rise of piezometric head, because piezometric head at location 2 will be more than piezometric head at location 1. So the whatever the rise is there, this value is given as 10 mm. See, 10 mm value they have given here, correct? 10 mm value they have given for this one. Okay. Now see, for the sudden expansion case, if you remember the formula for sudden expansion case is V1 minus V2 whole square by 2G. Correct? Now again relation will be in terms of V1 V2, use continuity equation. A1 V1, A2 V2. Now you will have a relation between V1 and V2. Using equation 1 and 2, you will get the answer. So this is equation 1, this is equation 2. From 1 and 2, you will be getting another velocities, and then after that you will get the answer also. Correct? Do it fast, guys. What will be the answer for the discharge? Okay, so it's like a same question only, but what is given? HGL rise. So that data you should be able to utilize in the equation also. Otherwise, it is what very difficult to understand the question, right? And also the point is, you should understand what HGL means. You should know what is the meaning of HGL. Pressure head plus datum head. This thing you should know. Then only you will be able to calculate the answer, right? So if you solve this one, finally the discharge will be coming out to be 0.03, approximately 0.0327 meter cube per second. You can check your answer also. Okay. Now moving to the next question, guys. This one. Now in this case, coefficient of contraction they are asking. Horizontal pipe suddenly reduces, sudden contraction case from 0.5 to 0.25, due to which pressure changes from 135 kilopascal to 110 kilopascal. If the flow rate, okay, flow rate is directly given, calculate the coefficient of contraction. Do it fast. Do it fast, guys, everyone. Discharge they have given directly. Okay, so discharge given, dimensions or the diameter is given, we can calculate the velocities also, right? So simply try to understand the point. If it is reducing, okay, like this. If it is reducing like this, correct? Now, so here it is 0.5, here it is 0.25. Now, how I can apply the Bernoulli's equation? Simply see, Z1, Z2 will not be there, so I will not write those things. Simply loss. Okay. So sudden reduction formula you should know. Okay. P1 and P2 values are given. Okay. Now for V1 and V2 discharge is given, no? Okay. We can calculate V1 and V2 also. And what is the head loss here? V2 square by 2G 1 by Cc minus 1 whole square. Okay, you will get the answer here. So putting all those values, you will get finally the Cc answer also. So if I see, final answer will come out to be for the Cc is 0.689 approximately. This will be the answer. 0.689. Correct? 0.689 will be the answer. Correct. So all those are the what basic question if you know the points regarding the HGL and TGL, right? Now, one more time, I will just remind you regarding what are the details we have discussed regarding HGL and TL. HGL is the line which consists of all the piezometric heads. So if you plot the piezometric head along the length of the pipe, you will get the HGL. And if you plot all the total energy heads along the length of the pipe, you will get TL. Now, if I talk about the open channel flow, what will be there? Let's suppose this is a case of open channel flow. Okay. Fluid flow is like this. Now, for the open channel flow, what will be there? Pressure here, it will be what? Same. Everywhere the atmospheric pressure will be acting. Everywhere atmospheric pressure will be acting. So, you will see the HGL here itself. But obviously, TL will be like this. And the vertical intercept between them is what? The kinetic head. If I talk about like whether they will intersect or not, you should understand a very important point. If they are intersecting at that point means kinetic head is 0. Kinetic head 0 means velocity 0. It means the flow has stopped. Are you getting the point? Very, very interesting point here. If TL and HGL will intersect, what is going to happen? What is going to happen? The kinetic head will become 0. Kinetic head becomes 0 basically means the velocity is 0, and if velocity is 0 means the flow has been stopped. So in the case of open channel flow, whatever the fluid surface is there at that location only, you will have a HGL. Okay, because it is not a pressurized system. But for the pipe, we know the pressure is what? Somewhat more than the atmospheric. It is pressurized system in the pipe flow. So that's why you will have the pressure, static pressure here, somewhere here. Okay, so datum plus static pressure location will be here itself, right? Now, but in the open channel flows, you should remember the point. For open channel flow, this HGL will be the surface of the fluid itself, as the pressure everywhere is what? Atmospheric. So that's why it is HGL only. But the TL will decrease along the length. Okay, wherever the fluid flow is there, so TL has to decrease only because of the losses. And secondly, if both the lines whether intersect or not, it will not intersect. If it is intersecting, the flow will stop because the kinetic head becomes 0. That means velocity is 0. So I hope like all the doubts are clear for everyone. Okay, and remember HGL will be on the surface if it is open channel flow, but for the pipe flow, it will not be at the surface or at the pipe wall. It will be much above as compared to the pipe wall because it is a pressurized system, right? This is a case of pipe flow. This is the case of pipe flow, right? This is a case of pipe flow. This is a case of open channel flow. Both are different. So it is pressurized system and it is having a pressure, atmospheric pressure everywhere on the surface of the fluids. That's why it is known as open channel flow. Correct? So I hope this session is like very fruitful for you. And also you have understood all those concepts of HGL and TL. In the upcoming lectures, we will discuss the pipe in series and parallel and we'll solve those questions which already in the GATE examination they have asked regarding series and parallel and whatever the questions regarding flow through pipes, right? So if any doubt is there, you can mention in the comment box also. And let's suppose if any previous topic you have not covered, you can just go to the playlist, okay, and you can see previous all lectures that we have covered till now regarding the fluid mechanics and also for other subjects also, right? Thank you so much.